All right, hi, I'm Nick Rodriguez. I'm in Dr. C. Prasad and Dr. Crawford's research group. And with funding from Lawrence Livermore National Laboratory, we are developing a large volume, high viscosity stereolithography printer. So we're building this printer intending to print with high viscosity or paste-like resins with the material properties that you can see on left. Notably, we want to print with highly elastic, strong parts that have high temperatures they can operate at, and we intend to build complex geometries with a footprint of 400 by 400 millimeters squared. And this is building off of prior work that we did at Lawrence Livermore, printing UV curable silicones, which you can see at right. So our material choice stems from the tendency for traditional radical initiated polymers to be stiff and brittle when cured. More recently, there's been work into SLA printing with elastomers such as polyurethanes, which do have the material properties that we desire, but silicones tend to operate at higher temperatures and also have better understood aging behavior, which has led to their widespread adoption in industrial uses. We have previously investigated UV curable silicones with a thiolene radical-based curing system, but we observed pretty poor high temperature aging with this chemistry. So we are instead looking into adapting the traditional method of curing silicones, namely a platinum catalyzed hydrosylation reaction, adapting that to be UV curable. There has been some work in using UV to cure these types of systems, but it's been using relatively low intensities with curing times on the order of minutes, preventing its use in AM. So for the large areas that we're hoping to cure with, the high intensities that would be required for short layer times prohibits the use of laser-based or other DLP techniques that are used or available in stereolithography. And we need to develop a new method of patterning light over a large scale. So our solution is using a UV backlit LCD monitor with the film polarizers replaced with wire grid polarizers. You can see a schematic on the right of how an LCD functions with two orthogonally oriented polarizers that each only transmit one polarization of light, sandwiching a layer of liquid crystal. Any pixel of the liquid crystal that's energized will rotate the polarization of light, allowing that light to transmit through the second polarizer. There are multiple SLA printers on the market that use LCD screens to pattern UV or near UV light. However, these printers are highly limited in the types of resins that they're able to print with due to the low transmittance through LCD screens, even monochrome LCD screens. You can see some transmittance data for film and wire grid polarizers in the bottom left-hand corner. And you can see that wire grid polarizers transmit light at every wavelength in the UV, near UV region much more efficiently than film polarizers, even down to 365 nanometers. In addition, since wire grid polarizers are reflective polarizers rather than absorptive polarizers, they don't heat up as rapidly under illumination, allowing you to illuminate the LCD at much higher intensities without overheating the screen. So these features were cured with an LCD that had the film polarizer proximal to the light source replaced with a wire grid polarizer. This LCD had 75 micron pixels, and we were curing a PR48, a relatively easy to cure acrylate resin. And we were curing lines ranging from 2 to 10 pixels and holes 5 to 20 pixels. The smallest lines and holes we were able to resolve were 300 and 680 microns respectively. And these features were overcured from what we intended, although we were able to get features that more matched the intended features when we cured with lower intensities. We just failed to resolve the 2 pixel line at these lower intensities. So on the right, you can see the whole printer assembly, where the light patterning components that I just discussed would be illuminating in an upwards direction from below the release film. That's not pictured in this image, but it is there. This type of printing, since we are intending to cure paste-like resins, we can't use a resin bath like is typical in SLA systems, because the stiffness of the uncured resin often exceeds the stiffness of a cured elastomeric structure. So rather, we are coating 500 micron layers of resin on the release film, each layer, using a slot die coater and a progressive cavity pump. And you can see on the left, the entire printer is enclosed in a UV-proof enclosure. So the release film onto which the resin is coated is wound between two rollers that can control the tension in the film. To coat each layer of resin, the film translates to the left while the slot die coater is extruding a line of paste, spreading it into a film of about 500 microns. After the curing step, which again is illuminating from below that film, the rollers detension the release film, allowing the part to be raised up without exerting any force onto the cured layer. At the desired layer height, the rollers will retension and initiate separation. And by peeling off the release film from our cured structure at these high peel angles, we're able to decrease the separation force by over a magnitude compared to if we just tried to lift the part straight off of tension Teflon. You can see our 385 nanometer LED array at left emits a light field of 2000 milliwatts per centimeter squared over an area of 400 by 400 millimeters. And at right, our slot die coater there is recoating a resin it can recoat viscosities exceeding 200 Pascal seconds or 200,000 centipoise in about 500 micron layers. And this was our first full-scale 2D patterning of a resin. This is another Acrylate radical-based resin, and the pattern is about a foot per dimension with features as small as a few millimeters. So in addition to curing acrylate resins, we have also had some success curing the platinum catalyzed silicones that I discussed as the motivation for our work. That's seen at the top right, and the UT and Livermore logos were cured with an intensity of about 80 milliwatts per centimeter squared for 20 seconds, which is about 2 orders of magnitude higher flux than commercial resins typically need to cure. So curing these parts would raise the temperature of the LCD screen even after we replace the film polarizers with wire grid polarizers. It still raised the temperature of the screen to about 80 degrees Celsius. And so we've developed a COMSOL simulation to model that temperature, and we're exploring techniques to reduce the temperature of the LCD during printing. With a UV curable silicone, we hope to explore applications like inflatable structures and soft robotics that you see in the top left, as well as printing graded density lattices to have a pressure distributing prosthetic socket liner that you can see in the bottom left. Finally, we hope to develop a series of design guidelines to investigate the resin deflection during printing based on the resin stiffness. And so finally, I would like to again thank Lawrence Livermore National Laboratory for funding this work, and I look forward to answering any questions now or during the poster session.